Good morning. About to start our first day of the week off, continuing on with factoring. I think maybe I started on this on Thursday and Friday. So today I'm just going to go into some special factoring cases. This one is called the difference of two squares. So this is how I always like to begin my discussion on what a square is, right? So I like to do this visually. So if I arrange these dots right here, I have one dot. The next one I have 4 dots, right? After that, that's 9 dots. And right here is 16 dots. At this point, you probably could get like your students or whoever you're trying to grasp onto this concept to see if they can catch a pattern, maybe complete 3 more of them and make them count it out, all right? So what happens is you kind of start them off with the numbers here, see if they can catch on to the pattern and continue maybe about 3 more. At that point, you can talk about what a square is. We call these particular numbers squares because if you look at the shape, they create a square shape, all right? So you got 1, you have 4, 9, 16. The one after that will be 25, then 36, then 49, 64, so on and so forth. So basically, if you multiply 2 times 2, you get 4. Just like a 3 by 3 is 9, a 4 by 4 is 16. And therein lies your definition of what a square is. A square is when you take a number and multiply it times itself. Or if you take a quantity and multiply it times itself, it is also considered a square. All right, so difference of two squares is a special type of factoring pattern. Difference indicates subtraction. And so that means the difference of two squares means you'll have a square minus a square. But remember, in mathematics, a square is not just a shape. It's a quantity, it's a way that we can calculate. So this is just like a visual representation of what the words are saying. The textbook definition of that would be a squared minus b squared. Because remember, anytime you raise something to the second power, that's considered a square, minus something else raised to the second power, that is also a square. All right. So when you see a square minus a square, what you're looking at is a second power minus another second power. All right, so if I have a square minus a square, difference of two squares, the way that this is factored, super simple. If you pay attention to what's in that box, I have an A and a B in the box. Basically, that's what's going to go inside of the parentheses, an A and a B, an A and a B. You can put plus on one and minus on the other. Or you can just say minus plus, either or. Bottom line is you get AB with 2 opposite signs in the middle. That's it. The reason why this works goes right along with the definition that I stated the other day. When you multiply 2 factors together, you'll get a product. So if I factored those things correctly, that means if I multiply them together, it'll bring me back to what the original problem said. All right, so I'm going to use an area model where I arrange everything inside of this box here. A times A. Remember, we're multiplying everything. A times A is A to the second power. A times a negative B is a negative AB. A times a positive B, or B times a positive A, is a positive AB. And then if I do a positive B times a negative B, I get a negative B to the second power. Now, if you pay attention to these 2 boxes that are diagonal from each other, this one is a positive AB, that one's a negative AB. The only thing I'm left with is A squared minus B squared, which should bring me all the way back to where I started over there. So that's why it works. The only thing that can technically give you an issue or a problem with getting this correctly is if you don't know your perfect squares when you see them. So if you don't know what they are, you should start to get familiar with your multiplication facts, like what's 1 times 1, what's 2 times 2, what's 3 times 3. I suggest that you know all of them all the way up to like maybe 15 times 15. Like you should know those when you see them. So, because if you recognize them, then there's nothing to it. But you have to be able to recognize those numbers first. So here's my first working example. I have an x to the second power minus 100. Remember what I said, you have to be able to recognize certain numbers because they're not going to look exactly like this. Like you're not going to see this second power every single time. So it's up to you to understand that we're looking at a 10 to the second power when I say 100. And then over here I have an x to the second power. Now they start to look alike. And once you understand what's inside of those boxes, it should be automatic. You got x times x. You got 10 times 10. You put a plus on one, you put a minus on the other, and it's done. That's all you have to do. Second working example. And I'm keeping these as basic as possible. Later on in the week, we're going to start connecting this to like greatest common factors and some other stuff. But I just kind of want to make sure we understand the basis of what's going on here. So I have a x to the second power minus a 900. Once again, that 900 needs to be written as a 30 to the second power. We already have an x squared. So once you see those boxes, remember, now they look alike. That means when it's time for us to write our factors, we know that we're going to have an x times an x, and we're going to have a 30 times a 30. Plus on one, minus on the other. Done problem. That's pretty much the examples I wanted to go over for today. So the difference of two squares is really straightforward. The reason why I like difference of two squares is because you really don't have to think as hard about your numbers. Whatever you get in the first parentheses is pretty much what you're writing in the second parentheses. You just put a plus on one and a minus on the other. So it keeps it kind of straightforward. You can, once you get good at it, you'll be able to do that one automatically. You won't even be thinking about it. You could literally just go into like a zone and just knock those out. Only if you can recognize a perfect square when you see that number. All right. So if you run by numbers and you're not sure, like say for instance, you have 1 times 1 and you have it memorized all the way up to 15 times 15. So like if you get numbers that are higher than that, maybe you're 16 times 16, 17 times 17, multiply it out by paper just to check and see whatever your result is. And the more you start going outside of the ones you memorize, you can start adding that to your list of squares that you know off the top of your head. All right. So, it's just practice. Practice your multiplication. Start getting those perfect squares up here so you won't have to think about it so hard later. Because all you really have to do is recognize those numbers and then you can split everything up properly.